So in this series of videos, I'm going to be introducing you to the idea of the derivative of a function. And for this, we're revisiting what we did in our last section of the last unit of rates of change. We had talked about how the average rate of change is the slope of the secant. It's the old school slope that you're used to by just finding the slope between 2 points. And then we introduced the idea of how we can find instantaneous rate of change, which we said is the slope of the tangent, where we're using 1 point. However, the way we got around that is we said, well, we can't actually find the slope with only 1 point, so we're going to take that point and pick a second movable point close to it, and then move that second point until it's infinitely close to the point we care about, so that we can find the slope between our given point of tangency and the movable point. And then as we move the movable point closer, it gets so close we say, well, it might as well be the point of tangency. We can also call that the slope of the curve, since we're only at 1 point on the curve. But what I want to introduce to you is the idea that we also can call it the derivative. And this is a word you're going to be using a ton from here on out, derivative. But it is interchangeable with all these other names. So I may say derivative, but you can think of it as slope of the curve, or slope of the tangent, or instantaneous rate of change. Or I may see a problem that says slope of the tangent, and it's easier if I think of it as derivative. Or I can see a problem that says instantaneous rate of change, and it's easier to think of it as the slope of the curve. You will get used to being able to switch between the names, but a key thing when solving problems with this is sometimes just changing the name gives you an idea of what to do. But that's not what these videos are about. These videos are just about what is it when I say derivative. So the whole idea of it is that I have, let's say I want to find the slope for a tangent for the function g of x equals x squared at some unknown value of x. Well, to do this, I do need a point of tangency. Well, since I don't know the x coordinate, I'm going to keep it x. But then the y coordinate has to be on my function, so the y coordinate is going to be x squared. So if I'm thinking graphically, here's my function, and I'm just picking a point. Here's x, which makes this x squared. But then I want to pick a second point, a horizontal distance of h away, so that that x coordinate will be x plus h. And then to get the y coordinate, I plug that into my function. So I'll have the quantity of x plus h squared for the y coordinate. I can then move to finding the slope between those 2 points. So I have the change in y minus the change in x, or over the change of x. But that's still a slope between a secant. I need to move those 2 points closer together. So I will be taking the limit as the distance between them, h, approaches 0. In other words, as I move the 2 points infinitely close together. So I can go about, if I try substitution, I'm going to get 0 in the denominator. So I'm going to try simplifying. The bottom is just going to be an h. I can already see that x squareds are going to cancel, and I'm now going to be able to divide what's left in the numerator by h. So I'm left with the limit as h approaches 0 of 2x plus h. I can now try substitution again. According to the limit, h is the only thing that's getting changed. So I can think of x as a constant, although a constant variable sounds weird. But h is the only thing I can plug 0 into. So if I plug 0 into h, I get that this is 2x. So let's talk about what 2x means. What this tells me is that if I don't know what x is, the slope at that x value is going to be 2x. And that sounds weird to say, but it may help you to think of it as what this gives me is a formula for slope. So I don't need to go through this limit calculation over and over and over again for all the different x's I could possibly use. I now have a formula that says, okay, what if I wanted to know the slope of this function g of x when x is 7? Well, instead of going through all this calculation, I can just plug 7 in for x in my formula right here. Say, well, when x is 7, the slope is 14. Or if x is -3, I can plug it into this formula. The slope is going to be -6. It saves us time. But this idea is what we call a function, a derivative of a function. So what we were doing to find the instantaneous rate of change, we actually call the derivative. We call it the derivative. And this will give us an equation that tells us the slope of the curve for any x value that we're using in the domain. And there are kind of two versions of this. The version that I introduced you to at the end of last unit with rates of change is called the difference quotient. It is the definition of a derivative, and you are expected to know that that is the definition of a derivative. Obviously, I don't expect that you remember that right away. We'll work on that. There is an alternative form that is still that I have written below here. This is still the slope between 2 points right here. So you can see change in y over change in x. But now to move them closer, I say that x has to approach a. So still change in y over change in x, and then move the 2 points close together. This is not used as often. Typically, this is going to be used if we're dealing with radical functions or rational functions, because it makes some of the algebra of simplifying it easier. When I get to doing some examples, I will do one of the examples this way.